Momentum is a vector quantity that is conserved in a collection of objects that is considered closed and isolated. A system is a defined collection of objects. No objects enter or leave a closed system, and no net external forces are acting in an isolated system.
This value was first defined by Sir Isaac Newton, who said that the quantity of motion of an object is equal to its mass times velocity. Therefore, momentum is equal to mass times velocity, denoted by p with units kilograms meters per second.
According to the impulse momentum theorem, change in momentum is also equal to force times the amount of time of the collision.
All the stuff we've been talking about so far has been about 2D collisions and momentum. But as you guys already know, physics isn't straightforward.
2D momentum concepts are analogous to rotational ones as well. Mass, which is an object's resistance to movement, is now moment of inertia, an object's resistance to rotational movement.
Velocity's rotational analogy is angular velocity, and force's counterpart is torque. Stupid physics, always resisting simplicity.
Using these concepts, you can apply 2D momentum formulas and concepts to rotational situations. Angular momentum is denoted L, which equals rotational inertia or moment of inertia times angular velocity with a curly W.
Momentum is conserved when there are no external forces acting upon the system. This conservation occurs in 2D momentum as well as angular momentum.
In 2D, the formula for momentum is mass times velocity, and the total final momentum of all objects in the system must be the same as the initial. Logically speaking, a boulder rolling down a hill has more momentum than a bag of leaves. This is because more mass constitutes to more momentum.
When the force is zero, no force on the system, then the impulse is zero. Thus, there is no change in the final and initial momentum, and it is conserved. Here's a practice problem for 2D momentum. Vishal's 900 kilogram truck is going 30 meters per second east, and Tanuja's 1200 kilogram truck is going 40 meters per second west towards Vishal's truck. When Tanuja's truck hits Vishal's truck, they stick together and move in one direction. What is the final velocity of both of their trucks?
Since momentum is conserved in this truck system, you can set up an equation with the momentum formula P is equal to mv. Setting up the original situation with the two separate masses m1v1 plus m2v2 and setting that equal to the final, which is the sum of the masses m1 plus v2 times the final velocity. Solving for final velocity, you can get 10 meters per second as their velocity they travel in the west direction. In this example, we will use hockey pucks to demonstrate this concept.
The white hockey puck is at rest initially, while the red puck has an initial velocity towards the white one. When the red puck hits the white puck, both go off in different directions, in different speeds.
But remember, since there is no external force applied on the red-white puck system, the total momentum stays constant.
This concept applies to angular momentum as well.
Angular momentum is an object's circular momentum about a point. Angular momentum is similar to 2D momentum, but instead of mass, it has a moment of inertia, and instead of linear velocity, it has an angular velocity.
Total angular momentum stays constant unless there is an external torque applied on the system. We can see this conservation in this video. When Tanuj brings in his arms, the point masses on the ends become closer to his center of mass, and his moment of inertia decreases while his angular velocity increases.
Since there are no external torques on the Tanuj book system, his angular momentum is conserved, even when he brings his arms closer. He also spins faster due to his lower resistance to motion and greater angular velocity about his center. After lengthy calculations of initial and final rotational inertias of the Tanuj book system, we found the initial value to be 2.347 kilograms meters squared and final 1.349 kilograms meters squared.
Using primitive methods of video analysis, we were able to calculate the amount of time it took for one rotation at the initial and final positions. Dividing 2 pi by those values gave us the angular velocities of 2.464 radians per second for initial and 3.879 radians per second for final.
Notice that the initial angular velocity is lower than the final because moment of inertia has decreased. Finally, using our belabored equation, moment of inertia times angular velocity to find total angular momentum, we found that initial is equal to 5.783 kilograms meters squared over seconds, and final to be 5.232 kilograms meters squared over seconds.
These numbers are pretty darn close, considering the error from assuming that Tanuj is a cylinder and hand timing durations of rotations play into the calculations.
Last night took a L, but tonight I bounce back. Wake up every morning, by the night I count stacks. Knew that it was real when I hit it, bounce back. You ain't getting checks. Last night took a L, but tonight I bounce back. Boy, I've been broke as hell, catch the check and bounce back. D-Town LAX, every week I bounce back. Whoa, if you